Okay, so it's 9:12, and we're finishing 3-1. We got 3 problems left on 3-1. The following question says, determine if the given graph is a one-to-one function. Now, here's the kicker. We've been looking at our things functions, right? And they have to pass a what? What do they have to pass? Vertical line test. So the criteria for a one-to-one is not only do they have to pass a vertical line test, they also have to pass a horizontal line test. So does this pass a horizontal line test? Yes or no? It does not. Ladies and gentlemen, do you see that right there? Yeah. Now, given this, and we could say, well, let's say for grins and giggles that this is a exponential that's been reflected, right? And shifted, and that's the asymptote. Yeah? But we don't know what type of function it is, right? They just say, here's a graph, correct? Yeah? So it appears to be a horizontal line. So a one-to-one says that no x's can repeat and no y's can repeat. That's the only way that it ensures that you'll never have a horizontal line. Does it make sense? Yes, ma'am, it came right off there. So if it's on your homework, guess what? It's guaranteed to be a possibility for your test. I mean, how did your chapter 1 test compare to the homework that you took? Was it straight from the homework? I don't make it up. I only see it when I review it. So, all right. It's a yes or no. Right. Determine if it's a one-to-one. It should be a no, because the x is repeated. You got a horizontal line, right? I mean, within that. So, yeah. Okay. The amount of garbage G produced by a city with a population P is given by big G equals F of P. G is measured in tons per week. A, the town of Tola has a population of 40,000 and produces 18,000 tons. No, 18, not 18,000, 18 tons of garbage each week. Express the information in terms of the function F of. So it would be what? F of 40,000 equals what? 18, right? Yeah? Okay, so part B, explain the meaning of the statement F of 60,000 equals 20. So what does the 60,000 represent, guys? Yeah, 60,000 represents the population. What does the 20 represent? The tons, the amount of garbage, right? In units of tons, right? Questions? Good? I've already turned down the air, but it is hot. They had something that happened down in that mechanical room down there. So, sorry. Hope your deodorant works. Okay, we're done with 3-1, right? Yeah? Sweet. So, 3-2. All right. Domain and range. Domain is all the x values, right? And if you write a domain, that is in interval notation. So you have parentheses and you have brackets, right? Okay. And if you remember, or if you understand functions, and in particular, there's what's called 6 basic functions, which happen to be a linear, quadratic, cubic, square root, inverse, and absolute value. those 6 basic functions, if you understand the characteristics of those, then you should be solid when you're talking about domain and range. Okay, so I can send you a PDF. Matter of fact, I'll put it up on the website. It says 6 basic functions. It's about 2 or 3 pages, but it goes through every basic function, and it tells you every characteristic: increasing, decreasing, max, mins, end behaviors, zeros, x-intercept, y-intercepts, domain, range. It covers everything, and it lists them out, and you can see it drawn because it's basically parent functions of everything. So, all right. If you're looking at a domain of a radical, then you're going to set it, the radicand, which is everything underneath the radical, to greater than or equals 0 and solve. And then you'll have the domain for that. So that's what it's saying down here. If there's a denominator in the functions formula, or if it contains an even root, set the radicand greater than or equal to 0, then solve. So some things in there. We'll go through that. Set builder or set notation. We've done that. Interval notation. We've looked at that, have we not? It's kind of putting the cart in front of the horse. We've already done this, right? We just got done doing this. And then they talk about it in the next section. It's kind of backwards. But anyway. Intervals, they're talking about open dot, closed dots. Unions, right? To combine all intervals in one set, which is an OR. Anything there? Piecewise functions. Hey, we talked about them the other night, do we not? We did. We said y'all used piecewise functions before in your life, have we not? You have where? Huh? Yeah, price breaks. Mailing letters or mailing a package, right? If it weighs a certain weight, you pay more, but there's a range of things that cost there. Piecewise functions, they're not as scary as what you think they are. They're worse. So no, they're really not. They're quite easy. But the key is looking at from where to where on the domain are we looking at this particular function. So we'll keep it to like linears and quadratics and stuff like that. So, and we'll look at how piecewise functions are sketched. So we'll look at that too. Okay, so if we look at this one, it says for the given relation, and the relation is a set of ordered pairs, right? Give the domain and range and indicate whether it is a function. Well, first off, in order to tell whether it's a function, our x's cannot repeat, right? So I got a 1, I got an 8, got a 9, and got a 3. I'm good. This baby is a function, right? So if I do the domain, does it matter if it's in order? Nah. We tend to put things in order. That's how we've been trained. Range, we have a 2, a 3, a 5, and a what? 7. So as long as you got all those there, then we're good, right? Okay, any questions on that one? Y'all really good on that? Sweet. Yep, domains are the x's and the range is the y's. Yep. Okay, so let's look at this one because I could have picked a slew of examples to use, but I thought we'd look at some that were at least useful on some things and allow you to look at different stuff. Find the domain and range of the function below using interval notation. Well, first off, does this function go on forever? How do you know? You have closed dots there, right? There's a finite ending point on that. So if I'm looking at domain, which is x values, right, then I'm basically only looking from here to there, from 1 to 7, right? Now, does it include 1? Yes or no? Yeah? Okay. So domain 1 to 7 includes 1, and it also includes what? 7. What always gets parentheses no matter what? Not closed dots. Open dots and infinities, negative or positive, right? Yeah. So those are guaranteed to have parentheses. Now, I'm going to tell you 2 questions that you can ask yourself when it comes to finding the domain. That if you'll ask yourself this, you'll be okay. And the question is, how far to the left does it go? That's the first question. Because the domain in interval notation, it's always written smallest comma largest, always. So it's never largest smallest. It's smallest comma largest. So if you ask yourself, how far to the left does it go? Well, it goes to who? 1. How far to the right does it go? It goes to just 7. Those are called leading questions. So if you ask leading questions like that on the domain, what do you think we'll ask for the range? Yeah. How low does it go? -3. If you were to give that ordered pair, would it be there? Is that a point on the graph? Is -3 a point? Yes, ma'am. So therefore, I would. Now, so how high does it go? 6. Is 6 included? Yeah. Okay. Questions? Yeah. A parentheses? A parentheses will always be on infinity, positive or negative, and it will always be on open dots. Okay? Always on open dots. All right. So let's look at this one. Does this go off the graph towards the right? Okay, it does. There's no ending point, so therefore we have to assume that it goes on forever. Right? So, how far to the left does it go for domain? That's right. -1, right? How far does it go right? Forever. What's forever? Infinity. That's right. Exactly right. There you go. Now let's look at range. How low does it go? Look at that. Man, y'all going to be rocking and rolling on this section. How high does it go? How high? Are you sure? I'm hearing infinity. I'm hearing 8. Are you sure? It's infinity. I'm just talking you out of it by looking at you. Don't let me do that. You need to be confident in your answer. Okay? Stay true, even if it's wrong. And if it's wrong, then we'll discuss it, why it's wrong. But if I can talk you out by looking at you, going, then you ain't set on whether that is what it needs to be. Know what you know what you don't know, and get your unknowns known. Have a reason why you said it was infinity. All right. We had this discussion earlier. 9 minus 3x is the radicand, right? That's everything under the radical. And it's an even root. How do I know it's an even root? It's a square root. The index or the root is an even number, right? So 2, 4, 6, 8. You can do this on. Okay, so they will always be greater than or equal to 0. Because if you look at the parent function for a square root, you're looking at 0 to infinity for the domain. Okay, from 0 to infinity. So it would be greater than or equal to 0. Now, so you don't have to worry about shifts and all that other stuff. You just take the radicand, set it greater than or equal to 0, and then solve it. No, ma'am, you don't worry about the 3. What does the 3 do? Amen. It gets in the way. That's exactly right. What is the 3, y'all? Because we're going to talk about shifts. That's a vertical shift, is it not? Think about what we're doing. We're taking some answer, and then, well, 3 minus that, right? If you flip that, put that at the end, it would be the negative 1 times square root of 9 minus 3x plus 3, right? But they normally don't put things like that on the end of radicals. Why? Anybody know why? They normally end radicals in the equation and never put anything behind it because you don't want to be mistaken whether that's part of the radicand or not. Anything that's happening needs to go in the front. That way you know it's not underneath the radical, right? Yeah. Where did I get that greater than or equal to? Okay. So here we go. If I look at the square root function, this is what it looks like. Okay, that's the parent function, square root. It starts at 0. Its domain is 0 to infinity, right? So as long as I take any radical, even root, okay, square root, fourth root, sixth root, eighth root, I will always set it greater than or equal to 0 because they do not exist for negative values. You cannot take the square root of a negative number or the fourth root of a negative number, sixth or eighth root, because those are imaginary, right? Y'all remember when we done those? Yeah. So that's why we're setting it greater than or equal to 0. So we'll go minus 9. So we got negative 3 greater than or equal to negative 9. Watch this, because this is going to get you. I am dividing both sides by negative 3. So ladies and gentlemen, what does it do to my inequality? It flips it. Negative 9, negative 3 gives me positive 3. So ladies and gentlemen, I'm basically looking at this, and I'm going which way? Y'all agree? Well, it needs to be a solid, right? If I'm graphing on number line, if I take that inequality and graph it, this is what it should look like. Y'all agree or disagree? Okay, so what would I put for its domain? Yay or nay? Don't shrug them shoulders. Lord, have mercy. I'm not ignoring the graph, am I? Which graph? Well, let me ask you. So what graph are you talking about? The one in green and purple or the one in black? The green and purple only tells me why I'm setting that radicand greater than or equal to 0. So that's the math theory behind it. Okay? The black one is graphing the solution. So theory, uh-oh. That's theory. That's why this right here happens. Okay? That's what allows us to say that. All right. I know this is underneath in the denominator. I'm very much aware of that. But it don't matter. We're still going to do the same thing. So what is the domain of this? Minus 1. X has to be greater than or equal to what? Negative 1, right? Because the smallest number that it can be underneath that radical would be 0. If you take square root of 0, you get 0, right?
Wait, can you explain the greater than or equal to on that again? So why is that?
Why is this greater than or equal to?
Yeah, why is it true? Oh yeah. Okay. All right.
Because of the parent square root function domain,
Will it always be that?
180%.
Okay.
All right, so that's why. But we're going to have a discussion. Because this says x has to be greater than or equal to negative 1, right? Correct? But if I plug negative 1 in there, what'd I get? 0. Okay. And what's the square root of 0? No. So basically, they're saying based off this, it's to there, right? Y'all agree? But mathematically, I say this. Why? Hmm? Yeah. Now, so I'm curious on how they're going to take this in the computer. If they're going to account for that restriction or not in the domain. Okay? If they don't account for it in the domain, then you're good with the bracket, right? But they should. Does that make sense why they should? That's right. But look where this square root is. It's down in the what? No, it's down in the denominator. And you got a variable in the denominator. Anytime you have a variable in the denominator, you know that there's restrictions, right? Places that are going to cause it not to exist. Negative 1 would make it not exist because square root of 0, that's 0 in the denominator. How can you have, what's the numerator? How can you have 9 parts and nothing? Can you have 9 parts and nothing? Oh, yeah. Yeah. You can't have it, right? It doesn't exist. So if it doesn't exist, then it's undefined. So mathematically, the purple is correct. Do you understand me? And do you understand why? No? Well, I didn't try the homework on this. Okay? So I didn't go and see whether they were. I know the purple is 100% correct because mathematically that is sound. Okay? Now my question that I don't know is, are they taking in account the restriction when they're looking at this domain or not in their answer? Does that make sense? Well, the only difference between it is a bracket and a what? Yeah, I don't know whether that's going to be a bracket. Huh? This one, parentheses. So they are including that in the. So I want you to be aware of that. Does that make sense? We would technically go here because if it was in the numerator, hey, it's going to take a bracket, right? But because it's in the denominator, then that's mathematically 100% sound. So make sure that you understand that. I don't know if I've done any good or if I've done more harm. So that's out. Y'all understand why that's out? Because we have a denominator. It's in the denominator, right? So there is a restriction. So it can't be -1, right? That's why it went from a bracket to a what? Let's see.
Okay, that's what I was curious on. I was like, what? But I see that.
I just didn't know how they were handling it in the homework. That's the question I didn't know. But they should have handled it like the purple, and she said that they did. Yes. What do you mean now? Why did we not flip the inequality on this one? Did we multiply or divide across it with a negative? No. That's the only time it would move or flip, okay? All right. Woo, Lord help me. All right, so this is pretty cool. You ready? It is. I promise you. Well, let's just look at it like this. X squared plus 6x plus 8. That's what type of equation? A quadratic. Yeah. And I'm starting to agree with Riggett. We had a discussion. Praying for, right? Yeah. All right, good. So let's just factor this, okay? We ought to be able to factor these. So A times C is 1 times 8 is 8. And then, so what are factors when multiplied will give me 6? No, will give me 8, but add together to give me 6. That's what? 4 and 2. So I have x plus 4 and x plus what? So I set them, so that's each one equal to 0. So x is -4 and x is negative what? 2. All right. Now, let's just hang on right there. Put a big old pause. A quadratic looks like a U. And its domain is from -infinity to positive infinity. Always, right? Why? It's like this. But it never comes back in. Does that make sense? It can be really steep or it can be wider. Right? So they do it every Friday, Saturday, Sunday in the fall. Whoa, quadratic! So listen to them. They're not saying touchdown. Read the lips. So it's quadratic. So anyway, that's what it is. You won't ever look at a touchdown ever the same again. That's right. So there. So that, and this is what I talk about, those 6 basic functions. Those are characteristics. The domain of quadratics all the way from negative infinity to positive infinity, period. So we know that. But look where our quadratic is. Where is it? Denominator. So we got some restrictions, right? It can't equal who? It can't equal who? Right? It can't equal -4 or negative what? It can't equal them, right? So how the heck do we write that? Well, we're going to go -infinity to -4, parentheses, right? Or -4 to negative what? 2. Or -2 to what? Infinity. So it can't equal these. It can't equal those. Because those are what makes it 0, right? And if you have 0 in the denominator, then you have an undefined situation. So that's a place where it doesn't exist, right? Yeah? Now, you want to nerd out for a second? You want to nerd out for a second? I'll show you something. Okay, so, dad journey. Clear, clear. So what was the numerator? 1 divided by, wait, divided by open parentheses, that's x squared, right? Plus 6x plus who? 8. All right, y'all ready? Graph. Zoom 6. See those asymptotes? Guess where those asymptotes are? -4 and where? Yeah, because it doesn't exist there, right? Asymptotes are lines that the function approaches but never touches, right? Does that make sense? So you could clearly see that, hey, it's going up, then it crosses over, then it's what? Back down, and then it's what? Does it again. So that's why I like the math modeling 1101, because you get to see things like that. And sometimes seeing is believing. Fair enough? Okay. Yeah, I'm going to use parentheses. Why? Nope. That computer give you brackets too. Why am I using parentheses for -4 and -2, guys? That's exactly right. See, if this thing was in the numerator, shoot, we'd be using brackets, right? Well, really, we wouldn't even be saying any restrictions, would we? We'd say negative infinity to positive infinity. Every x you ever choose will work, right? But when you put it in the denominator, then they just mess it all up for you. Yeah. Okay? All right, here we go. So we're going to piecewise, right? So here's the piecewise function. The first one is x squared minus 1. That's a quadratic. It's only good for values. This first one is only good for values from negative infinity up to 2 and including 2, right? And then the x minus, or negative x plus 2, which is a linear equation, is only valid from 2, not including 2, and up, right? So you'd have a solid on this yellow equation and an open dot on the linear one, right? Y'all agree? All right, let's see if we can't do this. Is that going to bother y'all? It's 75 degrees in here. Yay or nay? Just imagine yourself on a Twin Props taking a flight. You'll be asleep in a little bit, right? All right. So for the function defined here, find f of 0, f of 2, and f of 4. Well, first off, what you have to make sure you understand is, where does 0, 2, and 4, what equation does 0, 2, and 4 fall into, right? Where in the domain do they belong? Well, where does 0 belong? In the yellow or the blue? Which one? Oh, we're going to sweat. I can't hear you. Sorry. All I hear is humming. I'm halfway deaf anyway, so sorry. All right, so where's 0? Is it in yellow or blue? Are you sure? There you go. Yeah. Because I told you that your domain for the first one was negative infinity all the way up to who? 2 and including 2, right? So if we kind of think of it like this, hey, this joker right here, it's like negative infinity all the way to 2, right? And that this one is 2 to where? Infinity, right? So if I write it in interval notation like that, then it's a little bit clearer to where things go, right? The 0 and the 2 go in the first one, and the 4 goes in the second one. So I don't even have to calculate anything. At 0, what is my answer? What's f of 0? Negative 1. What's f of 2? Well, that's when x is what? 2. That's what? It's this one, right? Don't pick open dot, because open dot means it does not what? Exist there. What is f of 4? Go to 4, boom, there you go. That's what? Negative 2. And that's what it's asking you to do, is it not? That's exactly right. They give you a graph, you can pull that off. Go to that value on x, look at it up or down, see where that graph is, right? Yeah. Questions? What is difficult as you thought it was going to be, right? Oh, come on.
Wait, why do you do that circle in -4 or -2?
Which one? Here? This one right here?
Yeah.
Oh, I just showed where it intersected, right? At 4, boom, it's at -2, right?
Oh, okay.
Right.
Could I have chosen like -3?
No, sir. You wouldn't have chose -3. Why?
Oh, wait. I'm so confused.
All right. So go to 4 on the x-axis, right? Go to 4 on the x-axis.
Okay.
Now, look up.
Oh,
Do you see anything?
yeah,
Now look down. Where does it intersect? Where does 4 intersect that line? It intersects it at what y value?
-2.
That's exactly right.
Wait, but if you go to 5, it's negative.
Yeah. But we ain't asking for 5, right? We only asking for who?
Oh, between the.
Yeah, it said 0, 2, and what? Oh, I just wrote what the domains were.
Okay, never mind. I don't have my glasses with me, so let's see.
I wouldn't even thought the glasses thing. It's okay. Yeah. Okay. So can you? This one doesn't have a graph. So what are you going to do here? All right. So I'm going to give you 30 seconds. Let's see what you can do. All right, so some of the strategies are identify your domain, and then see which equation to evaluate in. Right. So. All right, so I identified my domains, right? Kind of written those out. So let's see, I got f of -6, right? Well, -6 falls between negative infinity and 3, so I'm going to use this one. So what is, that'd be 6 plus 1, which is what? 7? How many of y'all said -5? Anybody? When you substitute things in, make sure that you're putting them in parentheses to keep from making that simple mistake right there. 3 would be in the top equation, so that's -3 plus 1, which is what? That's -2. And of course, the last one, which would be 6, is in the bottom one, so that's x minus 5, so that's really 6 minus 5, which is what? 1. See my domain here? It's from values greater than 3, but not including 3. So 6 is what? Greater than 3, right? So it would be in there. So that helps you. That's a strategy that will help you. Because that's really the hardest thing about a piecewise. Knowing what domain, what's the domain for each one of those little pieces? And where is the particular x value that you're trying to evaluate or analyze, where does it fit? So, all right. Any questions on that? Oh, we got to graph it. Anybody know how to graph this one? Anybody remember how to graph? Huh? Well, let's look at it. Where did I start at? I'm going to do this one in green. So I start where? -2, right? That's my y-intercept. My slope is -4/3, right? And my b, my y-intercept's -2. If you remember, that's y equals mx plus b, right? So it's negative. So what I'm going to do is I'm going to go down. It's -4/3, right? So I'm going to go down 4, 1, 2, 3, 4, and over 3, right? So 1, 2, 3, 4, and over 3. Negatives go down and to the right. Positives go up and to the right. If you go right, you'll never go wrong. Fair enough? Negatives go down and to the right. Positives go up and to the right. So, well, that's, hold up. I ain't done yet. About to show you something. This is only good up to who? -3, right? But look what, I mean, I went down and I'm down here, right? But it doesn't even exist on this side, does it? So if I have to reverse it, what's the opposite of down and to the right? Up and to the what? To the left. So I'm going to reverse it. I'm going to go up, 1, 2, 3, 4, over 1, 2, what? 3. 1, 2, 3, 4, over 1, 2, what? 3. Now, you can't do this, but I can. That's an open dot at -3. Okay? And then I can get rid of this one, right? Or you can, all right, let's just show you. It'd be a lot easier. There. Um, I'm going to put where I'm supposed to stop at, right? Correct? Okay, so just bear with me. So I've graphed it, right? So, it's not going to exist right there, is it? Why? Because it stops at what? -3, right? Okay. So, I went down and right because the slope was negative, and then I looked at my domain restriction, and it didn't even, it wasn't even there because it stopped at -3, right? Yeah, I had to go back up and over. Yeah. If I'd have thought about it, then that's what I'd done. But so let's do, yeah, let's do that. That's -1, right? And we're going to go down 1 and over how many? Mm-hmm. So down 1 over 3, right? 1, 2, 3, there. And then we'll go up 1 and over what? 1, 2, what? 3. And you got to do this with a computer. How is it? Just curious. How is it when it's graphing? Comes to graphing, is it easy or
The dots connect and then the line.
okay? You just put it where the stuff is.
I just make this and this is right.
All right. So I want you to see something. I'm about to. I can do this. You can't. So does that make a little bit more sense? Do you see how I shaded, covered up what it really wasn't there, and then you can really clearly see how things are. Now, I highly recommend colored pencils or colored pens. I really do. And if you notice, if I'm working something, I'm switching colors. Why? Huh? Easier to differentiate the process through the solving method, right? I can call out specific steps and it draws your eyes to it as opposed to just it all being one color. So, all right. So there. That's how you graph it. Now, seriously, if I had to graph it on the computer, I don't know if I could. I'd have to graph it on here first on a piece of paper and then transfer it to the computer. Because I'd have little squiggly lines like that. All right. Questions? Yeah, I can. Wait, what does it ask? Oh, state the domain. Oh. What would be the domain on this one? Just curious. Since it asked, it would be what? Wouldn't it be that? There's an asymptote there. It doesn't exist at -3, right? Wouldn't that be the domain? There's my union, right? It's a whoppy jaw infinity, isn't it? There you go. All right. Y'all good? Yeah. You know how you get good at piecewise functions? You practice them, but you got to be good on the functions that they implement or that they use within them. If you're comfortable with linear equations, then it's not going to be any problem, right? But it just depends on if you're comfortable with that. Because have we graphed linear equations yet? No. So anyway, ready? All right, this should be the last one in this section, right? Man. Okay, so given what I have told you thus far, could you pick, if we say this, distance, oh, shoot. If this one's A, that one's B, that one's C, and this one's D, could you pick what graph goes with the piecewise that's there? You already know it. It'll get you 30, 45 seconds. Yeah or nay? Yeah, okay. All right, look at it, because this is really good to end on. For the answer is A. Can I explain why? All right, so the domain for this one is only for the first equation is between -1 and 2, right? But it has to be closed dots between -1 and 2. -1 has to have closed dot, 2 has to have closed dot, right? So A has it, B has open dots, right? And C has a closed dot, but an open dot on 2, right? But D has 2 closed dots. Hey, that's okay. So D and A right now, right? For -1, that's a horizontal line at -1, right? 2 is an open, 4 is a closed. So A has it, but does D have it? No, it does it too, but look at 4. 4 is open down here, right? So therefore, it disqualifies D. Right here.
If it has the or equal to under it means it's closed, right?
Uh-oh. Um, Dang it. Right there. If it's got the equal to underneath, then it's closed. And really, you're just looking at beginning and end on those, right? You got to worry about it. Yeah. Okay. So 3-2 is done. No more after that. Let's go 3-3. All right. Yay. And if you didn't pick up 3-3, it's up there. So I brought 3-2, 3-3, and 3-5 just in case we got through with a bunch of stuff. Now, I'm going to tell you something. This 3-3, um, it's going to give you fits. You know why? They've got problems in here that happen to deal with finding rates of change of unknowns. And that, my folks, is where it's going to kick your bahootie. I'm just going to go ahead and tell you. I wouldn't put those in there. I'd stick with just the numbers because you're not a math major. I mean, that's something for math nerds to nerd out on, right? Oh, right here. We're going to do it. You haven't seen it? Okay. Well, all right. So rate of change is change in y over change in x, right? That's what the little triangle means. It's a Greek letter, delta. Delta means change. So f of x and 2 minus f of x of 1, right? Over x2 minus x1. Guys, we have not, honestly, you have not seen it written like this, right? You haven't seen it. It's more normally been like this, right? Right? Okay. F of x is the same as what? Y. So don't let that crazy notation scare you. Do you understand? Don't let it get you. Okay. We're going to calculate the rate of change looking at different points and stuff like that. We'll look at local minima, and local maximas. We're going to look to see where things are increasing and where things are decreasing. Okay. I'm not sure. Okay, so they're doing, sometimes they'll go local minima or local maximum, which is local minimum and local maxima, and they talk about global, right? Have y'all heard that term? Global. They'll use absolute here. Absolute and global are the same terms, right? So you may have uh, been taught global maximum or global minimum, right? It's the absolute for here. So the locals are more or less. Let's talk about it like this. Y'all have been to the mountains. Yeah, you're looking out through there, and it's pretty, isn't it? And you see little hills that just keep doing like that, right? They going up and down, and then you get way up there. You've been on the peak, like the highest peak. Yeah, was it Kleeman's Dome? And at the highest point? Yeah, right. You can see I don't know 7 states, right? Into what they say. Yeah, 5 or 6, something like that. It's crazy. Yeah, a whole bunch, right, from that high. So that's a high point, right? That'd be like an absolute, right? Because if you look left and right, you ain't seeing no more mountains, right? But these locals, you kind of like, you down in here, you kind of, and you be like, oh, there's a mountain up there. Oh, there's a mountain up there, right? They're just little mountains, but they're not the highest mountain. How's that? That's what a local is. And local minimum is, it's a valley, but it ain't the lowest valley. It ain't the lowest output, the lowest Y value. Okay? An absolute would be the lowest point in that particular function. That's the difference between those. And we'll see it. Don't worry. All right, so we're going to start out. We're going to look at the average rate of change on this function on the interval specified. Now, I'm going to tell you, guys, these are x's. How do I know they're x's? See that word? Interval. Interval notation. So here we go. You're basically creating a t-table, guys. So you're going to evaluate it when it's -1, and you're also going to evaluate it when it's what? +1. So that's 5 minus 2, which is what? 3, and then what? So I got 3 and 3, correct? Yeah, I just plugged them in, right? Y'all agree with my calculations? Yeah? So if I look at the average rate of change, then I can look at it in terms of this. Y2 minus Y1 over X2 minus X1. So I can do 3 minus 3. Let's say this is group 2 and this is group 1. Is that okay? And then that would be, and then it would be what? 1 minus minus 1, which gives me a what? Plus, so that's 0 over what? 2. Y'all agree? Yes or no?
Yeah.
I just plugged it into the equation. Excuse me, into the equation. I think what I showed you the other day was um, do change in x and change in y. That's what? +2, and this is what? 0. So slope is changing y over change in x, which is 0 over 2, which is nothing more than what? 0. What does that equate to? What type of line are we looking at? Huh? Horizontal. Because look who ain't changing. Who ain't changing? No. The Y's. You're right. It's okay. The Y's not changing. So if the Y's aren't changing, that's a horizontal line, right? And anytime you have a change in either your X or your Y to be a 0, then you've got a special case. You've either got a horizontal line or you've got a vertical line. That's a dead giveaway. If there's no change in one particular coordinate, then you're looking at that. So the slope is 0. Okay. You've got parts over whole. So you have no shaded parts over 2 to choose from, right? Y'all remember the pizzas way back when? Yeah. Okay. Good. 0. Yeah. They're just saying for this interval, find the rate of change. And it's quadratic. So I know that, that it's going to come down. But they're only picking 2 points and connecting as though it's a straight line. That's the thing you have to make sure you worry about. All right. So if we can do it on an equation, we can do it on tables. So between 2002 and 2003, that's one. How much is this? That's you changing y, and there's you changing what? Because slope is changing y over changing x, and that's 2 over 1, which is what? 2. Y'all agree? No, ma'am, I didn't pick 2. How far is it from 249 to 251? 2. Yeah. And now they want us to go from 2002 to 2005, right? So how far is it from 2002 to 2005? That's how much? 3. And then they want us to go here, right? So how far is it from 249 to 243? -6. Why -6? It went down, right? You're going down the number line. So therefore, if we look at this one, we're looking at changing y over changing x. That is -6 over 3, which is negative what? -2, right? You could plug them into the equation, the formula, if you want to. That's fine. I just find it easier to look at the change. How's it moving? And then you're good. If it's going up the number line, if it's increasing, it's positive. If it's decreasing, then it's negative, right? For that particular value. And you always have to look and make sure that your signs are taken care of. Because you have a negative or negative, which is a positive, right? Yeah. What you got?
What's always confusing for me is which one's the X and Y.
Left side's X and right side is Y.
Always.
Yeah. For tables, yeah. Yeah. If you remember the T tables that you used to create, you'd put the X on the left and Y's on the right. Yeah. So that when you look at a table like this, it's the same thing.
Same thing. It's just
Yeah. It's just not going to say these are the X. It's understood that time is always an input, and that's a year, right? So the output's based on the year. All right, guys. Okay, so I'm not going to lie. I put that answer up there. You know why? So we could look at it. Because it gets confusing. Because if you try to do all this, you're like, oh my. And I want you to see what they're giving you as a worked out solution, right? This is what they're giving you, correct? But we're going to do it together. And then we got a couple more we're going to do together. So you're going to be good at this, but we're going to travel together on this journey. All right? So we're going to use f of a minus f of b over a minus b, right? Now, why did they do f of a minus f of b and a minus b? They're, bless you, they're choosing, they're saying that what? This is a and this is what? Yeah. Fair enough? Okay. They really didn't, did they? I guess it really matters. All right. We'll make one A and one B. Doesn't really matter, right? Y'all know what I'm asking? Does it matter which one is A and which one's B? Nah, it didn't matter. Because you remember when you're picking points, it didn't matter which one was group 1 or group 2. Do y'all remember that when you were doing slopes? You got the same answer. So one's A and one's going to be what? B. So what I'm going to do is I'm going to evaluate this -4 in this equation, right? To get me an output. Are you okay with that? So if I do that, let's just do this. And maybe it'll make a little bit more sense. So let's evaluate 3 times -4 squared minus 4. So what's 3 times -4 squared minus 4? So that'd be 3 times 16 minus 4. 3 times 16 is 48, right? 48 minus 4 is what? Yeah, 44, right? Questions? That's no different than what we've ever done, right? Like on the first problem, correct? And you remember, well, what was it, 2-6 or was it, yeah, I think it was 2-6 we did function notation, did we not? Somewhere around there, 2-5, 2-6, right around in there we did function notation. And we had some letters in there, did we not? So here we are. We're going to do it again, but we're going to do it with letters. So let's do it. Let's do it with green. So we'll say 3 times b squared, right, minus 4. Well, what's 3 times b squared? Yeah, 3b squared, right, minus 4. So my output for b is what? 3b squared minus what? 4. Huh? Those are my outputs. I'm just creating a t-table, right? I'm trying to follow suit than what we have always done. Well, here's an x, plug it in to find a y, right? So we're just going to kind of see if some things fall apart a little bit easier than what they have up here. Because I well, we'll get there. Trust me, we'll get there. You ready? Yeah, they tried to do a lot of stuff at one time. So I'm going to show you how to break it down. Fair enough? All right. So we filled out our tables. Any questions about our tables? About the red and the blue and the green? Anybody? Y'all solid on that? Okay, so let's use f of a minus f of b, right? Let's take it. Here we go. We're going to make this group 1 and this group what? Is that okay? Okay, so it's y2 minus y1 over x2 minus x1. Y'all agree with that? So here we go. So this is 3b squared minus 4 minus who? 44, right? Y'all agree with that? Okay. Now on the bottom, it's the x's, right? So it'd be b minus who? Y'all agree with that? All right. Now, I'm going to combine some things up top. 3b squared minus 48, right? And then I have b plus what? 4. Now, that is that's the rate of change. But is 3 divisible into 48? What you're looking at is the difference of squares that they're trying to get you to. So let's go up, and now I'll show you what I've done. Everybody's good to the red? Yes or no? Yeah? Did I lose anybody? Okay, so I want to explain from the red to the blue. All right. All they're doing is simplifying it. 3 will go into 48 16 times, right? So if I pull a 3 out, that's 3 times b squared minus 16. I'm trying to find something to cancel this down here. Okay? And this is a difference of squares, meaning there's no linear term, right? So your your 4 has to be positive on one side and negative on the other. So that's how I went from the blue numerator to the black numerator. Is anybody confused about that? Difference of squares for quadratic should be pretty standard, right? It's the square root of the first one, square root of the second one, and you put one term positive and one term negative, right? Parentheses. And then 3's out here. Look what one of these are. One of the factors happened to be a b plus 4, right? Which allowed me to cancel it out. So that's what they're kind of playing it on rational equations, kind of simplifying it. So that's what they want you to do. Is it intuitive? Nope. Not on your life. Other than you need to be aware that this is what they're looking for. Okay, whatever problem you're looking at up here in the red, this coefficient and that constant should be that should be a factor of that constant, right? The coefficient should be a factor of the quadratic, and you're going to get a difference of squares, and one of that should be that term there. All right. Now I think that's a little bit easier than, see that? I mean, it's there, huh? Can you see how they're progressing? This right here is crazy. I mean, you know how many steps they're doing right here? Whole bunch of things, right? And then all of a sudden they get to a 3 factored out with a b squared minus 16, which isn't hard to go from this one to 3 times b plus 4 and b minus 4. Yeah. But you see this right here? I'm not going to, sorry. I did. I did. Because there's a lot of steps right here in this, okay? So I just tried to make it a little bit simpler so that you know what you were doing. Because, see, we found 3b, here's 3b squared minus what, 48? So we went the black to the red, and the red to the blue, blue to the green, right? So, all right. So if you want to look at what they ask us, what is the rate of change, right? Find the average rate of change on the interval specified for real numbers b, b's real numbers, where b can't be equal to negative 4, right? So the reason it would be like that is because what would it do? What would it create down here? What would negative 4 create down here into 3 times b minus 4? A 0. Right? So they're just putting that restriction on it. All right, so here's your answer. Green, yeah. Mm-hmm. When you see the black up there, see my denominator? Wait. Oh no. Really shouldn't be, should it? No. They're going ahead and, I don't know. They put it in as a difference of what? Well, if they do that, then they're distributing that negative to the 4. Yeah. They're distributing, because that's a binomial, and they're distributing that negative 1, this right here. Let me show you. Right there. They're distributing that on to here. They've already taken into account up here to make it a negative 3. But if you say you're minusing, let's go back to, if you're minusing 3x squared minus 4, what does that really become? Thank you. Negative 3x squared plus 4, right? And that's what they're doing here. Does that? Yeah. Yeah, I don't recommend that.
-3 times like the parentheses -4 squared, and then minus in parentheses of the 4, right? And then all right.
Yeah, they're doing so many steps in one thing that it ain't funny. So that's why I put that up there as well. So you do it like this, you'll be fine. You have a better chance to be fine. Let's just say that. Okay. I really don't. I mean, look at this one. Lord help us. All right, so we're going to attack this together, okay? So here's what I want you to do. I want you to plug these into a T-table, right? Here's your X's. I want you to find me my Y's. That's the first thing, right? All right, go. Do you agree with my outputs, my Y's? I got negative 11 and H minus 11. Do you concur? Oh, I didn't do that, did I? There, 3H minus 11. Is that better? No, I didn't. What did I not do? I didn't show this, did I? So, there. There you go. Good catch. If I'd have done my little arches, I would have saw it. Okay, so now do you agree? Good. So, you ready? This is group 2. This is group what? So it's y2 minus y1 over x2 minus x1. Let's go green. 3h minus 11 minus negative 11, right? All over negative 2 plus h minus negative 2. So when you clean that up, two negatives make a what? When you subtract a negative, it becomes a positive, right? So that would be 3h over what? H, which is what? 3. Why? H is canceled, right? Not as bad as what you thought it was going to be. And that's the key. See, we didn't do anything different on this one than we did on the previous one, other than we had a quadratic, right? And we just kind of factored the quadratic. This was a linear one, so just be mindful if you got a quadratic. You probably got to factor it. And you'll probably end up with difference of squares. All right, y'all good on that one? All right, let's do another. Do we have another one? Oh, we do. Snap. Oh, my. And it's quadratic. What was I thinking? Okay. Whew. All right, I let you. All right, so that's what I got for my X and Y's. Do you agree? Um, when you take X plus H times X plus H, y'all remember the perfect square trinomial? Y'all remember that? A squared plus 2AB plus B squared, right? Y'all remember? If you square the first one, you put it down, square the second term, put it down, and then multiply them together. That's the xh times 2, right? Y'all remember that? We did that way back, I don't know, a couple nights ago. No, we don't on a Tuesday since we only meet on Monday and Wednesday. So you can expand, multiply the x plus h and x plus h out and get x squared plus 2xh plus h squared, right? I just done that quick multiplying because we've shown you that, right? So if I've shown you that and showed you how it works, then I'm going to use it. But you can still expand it if you want to. It's fair game. All right. Y'all ready? And this might be all we need to do us in for the night. Y'all good on your outputs, yeah? All right, y'all ready to do this? Let's do it. Yeah, all right. Yeah. Ready? So that's 2 and that's what? 1. So here we go. Y2 minus Y1 over X2 minus X1. So we have 3x squared plus 6xh plus 3h squared plus 4 minus 3x squared. What would that be? Minus 4, right? You got to distribute that minus through both of those terms. If you do not, then it gets wrong. You remember polynomials when you subtracted polynomials? You had a parentheses right there. You had to distribute. It's like a -1 being multiplied through there. So be mindful of that. All over, got to change some colors. Um, X plus H minus X, right? So that goes, right? That goes. Leaves me with what? 6xh plus 3h what? Squared over who? X plus h, right? Anybody see what we're about to do? We're going to take out an h, and we're also going to take out a what? Nope, a 3. Good. So if we do that, let's go red. So if we do that, we do a 3h, so that would be just 2x, right? Oh, my bad. Yes. Sorry. You're right. Saw it and just left it. So it's H. Okay, let's just pull out an H. Because that's really all we can do, right? So let's go back and let's go red. So we'll pull out an H, which would be 6x plus, yeah, if I can write it. I'm not writing it too good tonight, am I? All over H, right? What happens here? Yes, you do, man. Booyah! Winner, winner, chicken dinner! Yes. Okay. The hard part's already done because everything after this is just maximum, minimums, increase, decrease stuff, right? Yeah, it's really good. Okay, well, we have 5 minutes left, but we're done. Okay, so any, I got happy and took something off and didn't take it there.